Okay, welcome back. So last time, in the last lecture, we talked about some new ideas, work and energy, that allowed us to solve some certain types of problems that would have been very, very difficult for us to solve using Newton's laws. Say if the force were changing or something like that, or maybe we didn't know the exact form of what the force would look like, sometimes we could use work and energy and still be able to solve the problem for a certain amount of information, certain types of information that we wouldn't be able to solve very easily with Newton's laws. What we're going to do in this next section is introduce some more new ideas that will allow us to look at another type of problem called a collision problem. This brings us to the next section, section 7, which is entitled Momentum and Impulse. So first, let's imagine that we've got two objects that are bumping into each other. So two objects moving toward each other, bumping into each other, and then moving away from each other. Now, it doesn't matter if one of them is stationary and the other one comes along and hits it, if they're moving toward each other, if they're, like one is maybe moving away from the other, but the other one eventually catches up and hits it, doesn't matter. Let's just imagine they're at one point apart, they come together, they touch, they interact with each other, and then they move apart. So, let's imagine we've got some kind of situation like that. So, we've got two objects. Let's call them maybe object 1 and object 2. They are, let's just say, moving toward each other or something like that. Then they collide. So they interact with each other. And then let's just say they move apart. Okay, something like that. So we've got an initial situation where they're not interacting, and then they interact with each other, and then some final situation afterwards. Now, we notice that the final situation is definitely not the same as the initial situation. Say object 1 is maybe moving this way initially, that way finally. Object 2 is moving this way initially, that way finally. So the velocities of the objects change. If the velocities change, they must have an acceleration. If there's an acceleration, there must be a force acting on them. A force acting on object 1, a force acting on object 2. So we know there are some forces. Well, what do we know about those forces? Well, the force that object 2 exerts on object 1, we'll call that F1, so that's the force on object 1, from object 2, so we'll call that F12. So, and we know that that's a vector, so we've got F12 vector. That's the force acting on object 1. The force acting on object 2 from object 1, we'll call that F21, so that's the force on object 2 from object 1, and we know that's a vector. Okay, so we've got force F21. How do we know, or what do we know about the relationship between these forces? Well, we know that F12 must equal negative F21. How do we know that? Newton's third law. So from Newton's third law, we know that the force that object 1 exerts on object 2 must be equal and opposite, in other words, same magnitude but opposite direction, to the force that object 1 exerts on object 2. I think I said that right. 2 on 1 versus 1 on 2. Okay. Now, what does this force, or what does the magnitude of these look like? Now, we know this minus sign only is in terms of the direction. That tells us the directions are opposite. The magnitudes, however, are the same. So what does the magnitude of the forces look like? Well, let's just imagine we could sketch what this force looks like. So as a function of time, before they actually collide, so before they touch each other, so to speak, we would expect the force to be 0. Okay, very little force, or no force, if they're not interacting. And then after they move apart, so they have no force before they touch, they interact, there's some force in between them, and then once they come apart, we'll assume no force again. So no force acting on them after the collision is over. And then what does the force look like in between those times, in here? Well, we don't know, but it's going to somehow, it's going to increase and then decrease. That's not supposed to go backwards, obviously. Okay, it increases, decreases, some form. We're not sure what it looks like. Well, let's just imagine that we could define, during this time, let's imagine that we could take this force that changes, and let's say we could define some average force. So we'll define an average value for that force during that time interval. Okay, so this is average. So sometimes the average, the force is below average, sometimes it's higher than average. Now, what do we mean by the average? Well, mathematically, what we would mean is that the area under this average rectangle is the same area that's actually under the force curve. So really, the average corresponds to having the same area. In other words, like these little triangular parts over here have the same area altogether as that one. It's not quite drawn that way, but I think you get the idea. So we'll define some average force during that time where there's actually an interaction. Now let's imagine that this time that it takes, what we might call the collision time, that's the amount of time when the two objects are actually applying forces to each other. We'll call that delta t. So that's the collision time, the amount of time that the objects are actually applying forces on each other. Now, this time can actually vary to a wide extent. We can have all sorts of different kinds of collisions where delta t varies. For example, in this little collision that I just showed you here, okay, how much time do these things actually exert forces on each other? Well, a fraction of a second. They're only touching each other for a very, very tiny time. But another example, here's a photograph of two colliding galaxies. So we've got two objects here that are colliding together. Now, an interaction like this might take millions of years, maybe even billions of years. So here is an example of a collision that has a huge collision time, a huge delta t. Now, to be honest, the condition that we had zero force initially and zero force actually, that doesn't really apply here, but the main ideas that we're going to get will still hold. So the main thing is to realize that collision times can really have a wide range of values. Okay, so it's going to turn out that a very important quantity in looking at collisions will be the product of this average force with the time interval, delta t. This is what we call the impulse. And we'll identify the impulse with the capital letter J. Now, we're actually going to look at two different impulses. The impulse that object 1 exerts on object 2 and that object 2 exerts on object 1. So we'll use the different average forces. We'll use F12 average and F21 average, and we'll actually look at these in terms of vectors so that the impulse is actually a vector quantity. So just keep in mind, the impulse acting on object 1 would be the force acting on object 1 from object 2 times delta t, and the impulse on object 2, in other words, impulse J or J21, that will be the force on object 2 from object 1 times delta t. Now, because the forces are equal and opposite, the impulses will likewise be equal and opposite. So, while we can say that F12 equals negative F21, we can also say that J12 equals the negative of J21. Okay? All right, now, why do we need these? Why are these things useful, the impulse? Well, let's go back to the average force. let's look at the average force. Now, this could be either the average force on object 1 or the average force on object 2. It doesn't really matter. Okay, let's just say the average force. We know that the average force acting on an object, and now let's make an assumption. Let's assume there are no other forces acting on one of the objects. So, this is an approximation in general. So, let's say we've got these two objects bouncing off each other. Now, we know that they're exerting forces on each other. Are there any other forces acting on them? Well, yeah, there's gravity. Both have gravity acting on them, the weight. Maybe there's some air resistance or something like that. That is true. However, let's assume that during that collision time, we can ignore any of the other forces. Okay? So whatever else is acting on them, we're going to ignore those, and we're going to assume that the main forces affecting their motion during that collision time are just the interacting forces. All right? So anything else, we're going to ignore. So what does that mean? The average force is then the net force that's acting on the object. So from Newton's second law, we know then that that must equal ma average. And we know the average acceleration is the rate of change of the velocity, delta v over delta t. So that is delta v over delta t. In other words, that is the mass. The change in the velocity is v final minus v initial, and that is over delta t. Okay? Now, let's multiply both sides by delta t, and what do we get? Delta t, over here, we have F average times delta t equals m times v final minus v initial. But what's that? What is that on this side? The average force times delta t, that's exactly how we define the impulse. So that's the impulse. So the impulse is equal to this thing over here, m v final minus v initial. Well, let's multiply that out. What do we get? Well, we'll have m v final minus m v initial. There we go. Let me write that as a single equation. We've got J equals mv final minus mv initial. Okay, there we go. J equals mv final minus mv initial. Now, let's think about this for a second. We've got mv final, mv initial. We've got basically the same quantity here, m times v, but evaluated finally, and then minus that quantity evaluated initially. Well, this thing is a very, very important quantity, m times v. This is what we call the momentum. Now, actually, to be more specific, it's the linear momentum. We'll actually see another kind of momentum later on, but for the moment, we'll just refer to it as the momentum. It's the momentum of the object, or of one of the objects, whatever velocity and mass we're using. And the symbol we use for momentum is the letter P. Sometimes it's a capital P if we want to talk about a total momentum or something like that, or a lowercase p if we're talking about just the momentum of a single object. So this is the momentum of the object. Now, you might say, well, that kind of looks like something we've seen before, the kinetic energy. And remember, the kinetic energy was 1/2 mv squared. And they do kind of look a little bit alike. They both involve the mass, they both involve the velocity. But a couple really important things is, first of all, notice the momentum is a vector. So momentum has direction. Kinetic energy is a scalar. It doesn't have any direction. Okay? And then also, this is just linearly proportional to v. This is v squared. There's also a factor of 1/2 out front. Okay, but some main things, keep in mind, momentum is a vector, kinetic energy is a scalar. All right, now, what do we see up here then? How can we write that? Well, we can write this then as the impulse equals, so what's this? mv evaluated finally, that's the final momentum. That's the value of the final momentum that the object has, minus the initial momentum. And there we go. Well, that looks like something that we've seen before, something we saw last time. If you'll remember, what did we see last time? Well, we found that W was equal to KE final minus KE initial, the work energy theorem. In other words, when we do work on an object, that work goes into changing the object's kinetic energy. And whatever work we do, that increases the kinetic energy by that amount, so that the final is that much larger than the initial. In other words, you might look at it bringing this over here. We could say that KE final was equal to KE initial plus the work done. So whatever work we do goes into increasing that object's kinetic energy. Well, if this is the work energy theorem, what do you think this might be? Well, this is the impulse momentum theorem. What is this telling us? Well, something very similar to the work energy theorem. That if we apply an impulse on an object, that impulse goes into changing the object's momentum. Again, we could bring the initial over here, maybe make it seem a little bit easier. What do we have? Bring this over here. We have P final equals P initial plus J. In other words, whatever impulse is applied to an object, that impulse goes into changing the object's momentum, increasing it to some larger final value. Or, it's possible, just like with work, it could be a negative quantity. In other words, what do we mean by a negative impulse? We just mean an impulse in the opposite direction. We might have an impulse that could decrease the momentum, or just change its direction. Maybe it's in a different direction and end up with another momentum that's in a different direction than the original momentum. Okay, very, very good. Let's stick some numbers in here. Okay, let's imagine we've got a ball, and that ball is going to bounce off the tabletop, something like this. So let's imagine the ball has a mass of 10 grams. It's coming in at a speed of, let's say, 2.5 meters per second. And let's imagine it's at a 45-degree angle. So a 45-degree angle above the horizontal. It hits the tabletop and then bounces off again at 2.5 meters per second. And let's say again at 45 degrees above the horizontal. But initially it's coming down and then it bounces off and goes up. Let's look at the impulse that's being acted on the ball from the tabletop. Okay, so here we are. We've got a ball with a mass of 10 grams. Initially, it's coming down at 45 degrees below the horizontal, hits the tabletop, then bounces up at 45 degrees above the horizontal. Initial speed of 2.5 meters per second, final speed 2.5 meters per second. Let's figure out what the impulse is. Now remember, the impulse is equal to the final momentum minus the initial momentum. Now that's a vector equation, and we can always break vector equations down into components. So actually let's do that. So we'll find the x component of the impulse is equal to the x component of the final momentum minus the x component of the initial momentum. And exactly the same for y. The y component of the impulse will equal the y component of the final momentum minus the y component of the initial momentum. Okay, so let's do that. So here's our mass, here's our speed, here's our initial situation. What's the magnitude of our initial momentum? So our initial momentum is mv initial, which is the mass. Now what's the mass? That's grams. Let's put it in kilograms. So that will be divided by 1,000, 0.0100 kilograms, times VI, which is 2.50 meters per second. In other words, 0.0250. And what are the units? Kilogram meters per second. So that actually shows us what the standard SI units for momentum are, kilogram meters per second. Now, I'm sure you'll be glad to know there is not a separate unit for those, so we'll just leave it like that. Kilogram meters per second. So that's the magnitude of the initial momentum. Let's break down our Momentum into components. Let's define a coordinate system. Let's say that x will be horizontal to the right, y vertical up. Okay, so what's the x component? The x component will be this part, the y component will be that part. So PIX, P initial x, will be P initial, let's say, cosine 45 degrees. In other words, 0.0250 kilogram meters per second cos 45 degrees. We multiply that out, that turns out to be 0.0177 kilogram meters per second. So there's the x component. Now what about the y component? P initial y, that will be P initial, and the y component, this one, that'll be sine 45, but we notice it's in the negative direction, so that's going to be negative pi sine 45 degrees, which is going to be negative 0.0250 kilogram meters per second sine 45 degrees. Multiply that out, sine 45 is the same as cos 45, we end up with negative 0.0177 kilogram meters per second. There we go. So there is the initial y component. Now, what about the final values? Well, the final momentum, P final, will be, well, same mass, well, same speed, so the magnitude of the final momentum will be the same as the magnitude of the initial momentum. In other words, 0.0250 kilogram meters per second. Okay, now what about the x and y components? Well, the x component, P final x, breaking this down into components. We're going to break this down here. Here's the x component, here's the y component. So the x component will be P final cos 45. Well, since P final is the same as P initial and cos 45, we're going to end up with that same value. So P final x will be 0.0177 kilogram meters per second. Now, what about P final y? P final y will be P final times sine 45, but now it's positive. So P final y will actually be the same as P initial y, but positive rather than negative. So it'll be positive, again, 0.0177 kilogram meters per second. Okay, there we go. We've got all of our components. So what are the values of our impulse? Well, what do we get for Jx? Jx is P final x. Well, we've got all these terms here. What's P final x? P final x is 0.177 kilogram meters per second. So 0.0177 kilogram meters per second minus P initial x. P initial x is 0.0177 kilogram meters per second. And what do we notice? That exactly cancels out. So Jx is 0. What about Jy? Well, P final y is 0.0177 kilogram meters per second minus P initial y. P initial y is negative 0.0177. So minus a negative. So we've got minus a negative. Those don't cancel out, they combine together. Minus a negative is plus a positive, which leaves us with Jy is equal to, the final y component of the momentum is then 0.0354. 0.0354 kilogram meters per second. There we go. The x component of the impulse is 0. The y component is that. So we can actually write the final vector impulse as 0.0354 kilogram meters per second in the y-hat direction. So what does that mean? That means that when this ball bounces off the table is actually applying an impulse in the straight up vertical direction. So the table is actually applying the force, the average force, directly upwards. So it's basically kind of like hitting the ball so that it's coming down and then it's going up this way in the vertical direction. There's no horizontal force. We know there's no horizontal force because there is no change in the momentum in the x direction. The initial x momentum is the same as the final x direction, final x momentum, so there's no force horizontally. We can actually figure out what the force is if we knew how much time the ball actually spent in contact with the table. We could figure out what the average force is. Let's just say that the time for that collision was, let's say, delta t is equal to maybe 1/10 of a second. Now, we know the impulse was equal to the average force times the time interval. In other words, the force is the impulse over the time, which is then 0.0354 divided by 0.1. Dividing by 0.1 is the same as multiplying by 10, so we end up with then the average force is equal to 0.354. Dividing by a second, so we get kilogram meters per second squared, and we know a kilogram meter per second squared is a newton. So the average force is then 0.354 newtons, and we can actually write this as a vector equation in the y direction. So there's the average force that the tabletop exerts on the ball when it bounces up. Okay, very, very good.